Belum, baru starting. Belum. Okay.
Assalamualaikum warahmatullahi wabarakatuh. So now our group will continue to present about the probability theory in this risk assessment. So compared to group 1, uh, their method is more focused on the qualitative method. So in our group, we'll be focusing on the quantitative method, which is the combination of engineering approach and the mathematical technique. So in this probability theory, we assess the reliability of the instrument, meaning that how long can the instruments such as valve, pump, alarm can function over time. So this probability use the concept of Poisson distribution to analyze the reliability. Why use Poisson distribution? Because this Poisson distribution focus on the binomial distribution, which focus on uh, independent event, which is very suitable in our risk assessment. For example, in this risk assessment, we only have two outcomes, which is fail and success. And uh, but by the definition of independent events, meaning that, for example, if for event A, which is the first failure or success in our instrument, for event B, whether it is success or fail, it will not be affected by the result of the first event. So that is why Poisson distribution is very suitable in this probability theory. So here is the equation given. The equation is the reliability with the function of time, the RT. And in this equation, they use lambda. However, in the previous session that has been shown by our doctor, we use mu instead of lambda. However, it is the same thing. Lambda mu is equal to the failure rate, and t is time. So using this equation, we will subtract it with 1, which is the total of probability, to obtain our equation of failure probability. And using this equation, we differentiate it to obtain our second equation, which is failure, our third equation, which is failure density. Uh, and lastly, we integrate this equation to obtain our failure rate equation, which is also which is the failure density over time equation. So why do we do such work to just obtain the final equation? This is because uh, we need to obtain the failure rate of the components, the instruments, to assess the probability, the probability of its failure. Yeah. So I will invite my next presenter to explain more.
Thank you, Aiman. So I'm going to explain about the two types of assessment that we can do on reliability. So there are two ways that we can assess the reliability, which are by series or parallel configuration. So the reliability in series are known as OR function, and reliability in parallel are known as AND function. Reliability in series is actually means that failure in any component results in failure in the entire system. For example, if you have a system with 4 subsystems in it, if system 1 fails, means that the whole system fails. So in other words, all of the units in series system must succeed for the system to succeed. So the next one is reliability in parallel or AND function. So reliability in parallel in short means that at least one of the units must succeed for the system to succeed. So as an example, if you have if you have a system with 4 units in it, if unit 1 fails, the system still succeed. So in parallel system, all units must fail for the system to fail. By any means that if the 4 units in the system, if 3 out of 4 units in the system fails, the system still succeeds. But if 4 out of 4 units in the system fails, then the system fails. So to put another way, if unit 1 succeeds or unit 2 succeeds or any of the n units succeeds, then the system succeeds. Then the formula that we use for both reliability in series and parallel will be explained by the next presenter.
Okay, thank you, Aisha. So this is series vs parallel configuration. We start with the left one first. Parallel link of components. The failure of the system requires the failure of both components. Note that there is no convenient way to combine the failure rate. For this session, we categorize it into 3, which is the first one will be failure probability, which is P equals to P1 times P2. The second one will be reliability. R equals to 1 minus R1 will be times with 1 minus R2. And then the last one will be failure rate. Mu equals to negative ln R over T. And then moving on to series link of components, the failure of either components adds to the total system failure. So same goes with parallel. We have three category, which is the first one will be failure probability. P equals to 1 minus P1 and times with 1 minus P2. And then the second one, reliability, R equals to R1 times R2. The last one will be failure rate, mu equals to mu1 plus mu2. I think that's it. I pass it to the next presenter. Thank you.
Okay, thank you, Izian. So now I am going to present about another formula that we will use in our calculation, which is the mean time between failures, or in its short term is the MTBF, which is the time interval between two failures of the components. So this formula is used to determine the probability of the component or instrument to fail within certain period of time. So the advantages of using this formula is it can help us in decision making of equipment replacement and repairing, and it can also help us to improve the reliability of our instrument. So as you can see on the slide, the formula of MTBF is the integration of RT with respect to the time. So if you solve the equation, the final formula will be 1 over lambda or 1 over mu. And I think that's all from me. I will pass this presentation to the next presenter. Thank you.
Okay, next we going on to the probability calculation example, which is a reactor alarm and shutdown system. Okay, for the question, a schematic diagram of the safety system of a chemical reactor is shown in the figure below. The reactor contains a high pressure alarm to alert the operator in the event of dangerous reactor pressure. It consists of a pressure switch within the reactor connected to an alarm light indicator. For additional safety, an automatic high-pressure reactor shutdown system is installed. This system is activated at a pressure somewhat higher than the alarm system and consists of pressure switch connected to a solenoid valve in the reactor. In the reactor feed line, the system stops the flow of reactant in the event of dangerous pressure. The failure rate for the various components are shown in the table. The reliability and the failure probability are computed for each individual component are calculated assuming a 1-year period of operation. The results are also shown in the table. A dangerous high pressure reactor situation occurs only when both the alarm system and shutdown system fail. These two components are in parallel. So the main objective of this question is to find the expected year or time for the alarm and shutdown system to fail by using the reliability in series and parallel formula. So for the solution, I will pass it to the next presentation. Thank you. Yeah.
Okay, thank you, Farhan. So for the solution, there are 3 steps to calculate it. The first one is for the alarm system. The components are in series. So first we are going to calculate the reliability, where we will multiply 0.87 with 0.96 and then we will get 0.835. Next we will calculate the failure probability, where we will 1 minus 0.835 and we get 0.165. Next we will calculate the failure rate, the mu, which using the formula negative ln r, and then we will get 0.180 volts per year. Next, we will calculate the MTBF, which we will get 5.56 here. Next is for the shutdown system. The components are also in series. So we will use the same steps as in the alarm system. So after we calculate all of it, we will get the MTBF, which is 1.80 years. Next one is the two systems which are combined in parallel. So for this one, we will first calculate the probability failure, where we will multiply 0.16 426 and then we get 0.070. Next, we will search for the reliability and then we'll get 0.930. Next, we will calculate the failure rate, where we will get 0.073 volts per year. And then last, we will calculate the MTBF, which we will get 13.7 years. So for a reactor with an alarm system alone, a failure is expected once every 5.5 years. Similarly, for a reactor with a high pressure shutdown system alone, a failure is expected once every 1.80 years. However, with both systems in parallel, the MTBF mean time between failures is the time interval between two failures of the components is significantly improved, and a combined failure is expected every 13.7 years. So that is all from our group. Thank you.